let's check the dimensional consistency of this equation. But the problem is there is a plus sign in between. Now, is these two equations similar? Yes, it is ml square t square inverse, and this is also ml square t square inverse. So this is the dimensional formula for kinetic energy. We are not worried about the numbers, we are not scared of the powers, because we know how to deal with this dimension. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about units and measurements. So how to measure something, how an international system was made in order to standardize units, and all other things coming with that. So let us get back to units, measurements and other details. So I told you in the previous class, we will be discussing about MUDs, that is measurements, units, and now we are going to discuss dimensions before we get to significant figures. So we will be discussing about dimensions mostly in this session. So what is dimension? What exactly is dimension doing in this physics world? How we can use dimensions for our benefit? Everything will be discussed in this particular session. So what exactly are dimensions? Is it like length, breadth and height? Not exactly. We can say that dimensions are there for every physical quantity. For example, we have the physical quantities such as we have mass, we have length, we have time, and so on. That is, we have luminous intensity, we have electric current, we have amount of substance. We have the 7 basic quantities, and we have symbols to denote each and every one of them. And each of these quantities have innate dimensions. For example, we can say that mass has a dimension which is indicated by m. And length has a dimension which is indicated by L, and time has a dimension which is indicated by T. Most of the equations we use in our daily life, which is from derived quantities or just from fundamental quantities, all will have dimensions. So there will be dimension for some equations and there won't be dimension for certain other equations. So we are going to find out what are the dimensionless and dimension bearing equations, what are their differences, how to check if those equations are correct dimensionally, and what are the drawbacks of dimensions. So for example, let's take one equation, that is area of something. I'll say that the length of a scale is 10 centimeters. Then I can say that length of a scale is 10 centimeters. Then I can say that that particular equation or that particular element will have a dimension of just L, because there is only one fundamental quantity there, that is length. So I can say it has only one fundamental quantity, that is L. This is a dimensional formula. Again, this is too simple. Let's go into something a bit more interesting. Area. So area is equal to, let's say, length into breadth. Length into breadth. If I have a rectangle, length into breadth will be the area. Again, it is nothing but length multiplied twice. That is, if I am measuring a rectangle which has length L and breadth B, I can say that I am measuring length once sideways and length twice on the upper part or vertically. So I'm just measuring length horizontally and length vertically, which means I'm measuring length twice, which means it has the same dimensions of length only. So I can say that it is L into L, which means there is a power of 1 here, there is a power of 1 here. So I can write it as L raised to 2. So we can say that the dimensional formula for area is given by L square, because we considered the equation in order to find out what is area Then we substituted what are the basic fundamental dimensions involved, and then we condensed them and we wrote it as such. If you want an even clearer example, let's go into physics. We can say that velocity is equal to displacement divided by time. So displacement is nothing but length measured. So we can say that L or V is velocity, and we can say that L divided by time t. So L divided by time t is the dimensional equation or dimensional formula of this particular quantity. So one more thing to remember is that there are dimensional formulas and there are dimensional equations. The difference between a dimensional formula and a dimensional equation is that if we are just writing something like this, that is L by T. So this will become L T inverse. This will be the dimensional formula of this particular equation. So if I'm just writing the dimensions like this, I can say that this is a dimensional formula. This is a dimensional formula. But if I am relating a physical quantity like this using an equation sign or equating sign, equal to sign, then I can say that this particular quantity is known as a dimensional equation. That is, this will become, when this is in the denominator part, we have 1 and 1 only. When I take it to the numerator, it automatically becomes 1 inverse. So that is why I can write it as V is equal to L T inverse. This is the dimensional equation. Remember, if I'm only writing it like this, just with dimensions, I can say this is a dimensional formula. And if I'm using an equal to sign, I can clearly say that this is a dimensional equation. Don't forget the difference. If there is an equal to sign here relating a physical quantity and dimensional formula, then we can say that it is a dimensional equation. And if there is no physical quantity or equal to sign, we can say that that is a dimensional formula. Now we are saying that, okay, I figured it out. It is very simple. Are you sure you have figured it out? I ask you, what is the dimensional formula for this particular equation? That is, kinetic energy of a particle is given by half mv square. What will be the dimensional formula? But sir, you didn't teach us about anything that is related to numbers or fractions. Now I'm confused. Don't worry, I'm here. So, in dimensional equations or dimensional formulas, we are not at all worried about numbers or fractions or constants. Even log terms, exponential terms, and trigonometric terms, all of those we are not worried about because we are not even considering that. That is how dimensional formula actually works. We will not be considering numbers, constants, or any other dimensionless quantities. So we can say that this particular equation can be written as how many fundamental terms are here. First, we identify what are the fundamental terms. This is a constant, which means this 1 by 2 is not being considered by us. The next term is m, which is mass. So for mass, we will write m. And the next term is velocity squared, which means we just found out the equation for velocity, that is v is equal to x by t or displacement by time, or simply we can write it as L by t, or which is equal to LT inverse. So here we can say that it is not just LT inverse, it is LT inverse to the square. That is LT inverse squared. So what do? We just do normal mathematics. We just take the power inside and then we can write it as m L square T square inverse. So this is the dimensional formula for kinetic energy. We are not worried about the numbers. We are not scared of the powers because we know how to deal with this dimension. Again, any equation can be written like this. For example, take any equation in physics and we can check if it is dimensionally correct or wrong. For example, I'm taking the equation which is force, that is F is equal to ma. So m here is mass, a here is acceleration, and if it is falling down, it is acceleration due to gravity. The point is it is acceleration. So we can say that F is equal to ma, which means the dimensional formula can be written as, identifying the terms first, which is there is a term for mass and mass is given by m. So we can say there is an m, and then there is acceleration. So again, acceleration is nothing but a is equal to v by t. Not just v by t, it is actually change in velocity divided by time. But anyways, acceleration is equal to v by t. V by t is nothing but x by t, or we can simply say that d square x by dt square is the equation for acceleration. But in dimensional terms, we can say that this particular equation can be written as, we already know what is the dimensional formula for velocity, which is L t inverse. And now we have one more t, which is t minus. So basically it is L t inverse divided by t. So we take this t also to the upstairs and we can write it as t inverse into t inverse. Simple mathematical operation. If you have t inverse and t inverse, it will become t square inverse. So we can write it as m l t square inverse. So we have the dimensional formula for force. Now most of the equations you will see will be denoted in terms of mass, length and time. So it is okay, but there will be some equations which will also pose other basic fundamental quantities such as ampere. So for ampere, if I am writing the equation for electric current, then you have to use the term A. Like we are using M, L, T, like that, if we are using for electric current, we are using the term A, which is indicating amperes. And if you are using for temperature, we are not using T or small t or anything. We are using temperature indicator K, which is Kelvin. So for electric current A, for temperature is Kelvin, for luminous intensity it is CD. Like that, we will use different symbols. But most of your equations and dimension formulas will be just based on M, L and T. So we just figured out how we can use dimensions. That is, if we have an equation, I can say that, okay, I can figure out the dimension. So why do we use this? So we can use this in order to check if two equations are dimensionally balanced. So we can check the balance or the correctness of an equation. That is, I can check if half mv square, that is kinetic energy, is equal to potential energy, mgh. That is, this is kinetic energy and this is potential energy. It is said that energy has same dimensions, but we don't believe anything blindly because we are physicists and we are going to find out if these are dimensionally correct. So we can check the dimensional correctness of equations. We can check if two equations are dimensionally balanced, and we can check the dimensional consistency of an equation. Right now, we have two equations here which are in terms of energy. I cannot relate two different equations. That is, I cannot relate an equation for energy and equation for a term which is not expressed in terms of energy. I cannot do that. If these two terms should be dimensionally correct, then if these two terms should be correct, then I have to equate energy terms with energy terms, force terms with force terms, like so. And now we have the dimensional formulas. That is, for half mv square, we don't have to consider the numbers. So we are starting with mass. We have 1m for mass, and v square we already proved it is L into T raised to minus 2. So this is the dimensional formula for kinetic energy. Now what is the dimensional formula for potential energy? Same method. So here we also have one mass, capital M, and here it is g. G is nothing but acceleration due to gravity, which is nothing but acceleration. G is equal to a, that is acceleration due to gravity. And we saw that for acceleration it is nothing but L t raised to minus 2. And now we have one more term, which is h. H is nothing but height, which is measured in length. So we can say there is one more L, and together we can write it as m L square t inverse square. So this will be equal to this. Is it? No. This is mlt inverse. This is ml square t square inverse. What is wrong? The wrongness is in the calculation. That is, this particular is v square, and we did not consider the square factor here. That is where you can go wrong. I just wanted to point out where you can go wrong. That is, v is equal to x by t, which means it is L by t, that is LT inverse. And now when we square this quantity, that is, when we square this quantity, it should be L square t square inverse. So when you're doing this and thinking that this is very easy, I'll just write it down from my mind, things like this, that is, small simple mistakes like this can occur. That is why you always write it down first and then copy it. So there is no error in your dimensional calculus. So the error in this particular equation was, just because it was v square, I did not consider it was the whole square, I just took ml. But it should be ml square t square inverse. Now is these two equations similar? Yes, it is ml square t square inverse, and this is also ml square t square inverse. So these two equations are dimensionally balanced, which means they are dimensionally correct. So that is one way the question can come, that is, check the dimensional correctness of these equations or balance these dimensional equations. One more thing is that they can ask you to check dimensional consistency of an equation. That is, equations can be of different forms. Anything which has an equal to sign can be written as equations these days. So they can give you a mathematical function as an equation and ask you to check the dimensional correctness. For example, they can ask x is equal to ut plus half at square. This equation you will see further down in the chapters, but anyways, x is equal to ut plus half at square. Can you check the dimensional consistency? That is this equation dimensionally correct? You have to check that. So how do we check that? So let's check the dimensional consistency of this equation. But the problem is there is a plus sign in between. So what dimensional analysis states to us is that if there are numbers in between, you can ignore them. If there are constants in between, you can ignore them. If there are trigonometric functions or exponential functions or log functions, you can ignore them. And if there is a plus, minus, into or divided by sign, you just have to make sure that they are dimensionally consistent, that you can write it as ut is equal to at square. So when we are writing down the dimensional formulas or dimensional equations, I can write it like this. This x is nothing but displacement. So L is equal to, u is the initial velocity. So we know for velocity it is L t inverse into t. Into t, instead of plus, I'm going to write equal to. If there is plus, minus or anything, you just write an equal to sign. Then you write at square. So a is nothing but acceleration due to gravity. A is nothing but acceleration, and we just found out that it is v by t, or simply L t square inverse. So we can say that it is equal to L t square inverse L t square inverse into t square. So what will happen? We have to further condense this equation so that we can write t raised to minus 1 into t, that is minus 1 plus 1, which is equal to 0. So there is only L here, and now this is equal to LT inverse square into t square, which means minus 2 plus 2, which is also 0. So we can write L. So we can say that L is equal to L is equal to L. That is, dimensionally, this equation only has length terms in them. So we can say that this particular equation, that is ut plus half at square equal to displacement, is dimensionally consistent. That is, there is no inconsistency. If there was a t in this equation, or if there was an a in this equation, or L but m in this equation, this would be not dimensionally consistent. But we just proved that this particular equation is dimensionally consistent. So all this comes under dimensional analysis. That is, we use dimensions in order to find out what we use dimensions in order for several purposes. For example, balancing an equation, dimensional consistency, dimensional correctness of an equation, all those was just checked. And now, one thing you have to remember is that there is a rule regarding this. It is known as principle of homogeneity. That is, principle of homogeneity. This principle of homogeneity states that you can only add quantities which have the same dimensional formulas. That is, I cannot just randomly show up and say 2 kg plus 2 centimeter is equal to what? If I ask you this question, what will be your answer? Okay, you will write 4 kg centimeter. That is a very good blunder, a beautiful blunder, because you cannot write it like that. You cannot write it like that. That is not how units and measurements work. So actually, there is no answer to this question because these are two separate terms. I cannot add one potato and 1 meter length. I can add one potato plus one potato, then there will be two potatoes. But I cannot add two different quantities. I cannot add kilograms and centimeters like this, or two different quantities or two different dimensional quantities cannot be added. The answer to this question is that it is non-existent. That is, you cannot add like this. What principle of homogeneity states is that only quantities with same dimensional formulas can be added. But the rule is that only quantities with the same dimensional formulas can be added. You cannot add two different units together. That is the only rule that principle of homogeneity is stating towards us, and we have to obey that. So this must mean that dimensional analysis is sweet. That is, there are a lot of applications to it. We can apply that to find out the dimensional consistency. If two equations are dimensionally accurate, if it is balanced, we can find out dimensions for everything. So it is like very good, right? Not really. So there can be a question that is asking, what are the drawbacks of dimensional analysis? So what are the drawbacks or weak spots of dimensional analysis? So first drawback is that we can only check if an equation is dimensionally correct. That is, if I write F is equal to MA, MA is equal to 5 by 2 MA, that is, we know that F is equal to MA, that is, force is equal to M into A. If I write MA is equal to 5 by 2 MA, this particular equation in itself is wrong. That is, this doesn't make an actual sense. It does not make any sense. Here also there should be a 5 by 2 for this equation to be correct, or any quantity that is balancing this particular equation. But if we take the dimensional analysis of this particular equation, it will be dimensionally correct because we are not considering the numbers, ratios, or any other factors. That is, if this particular equation is actually wrong and dimensionally correct, if we plug this into dimensional analysis, it will say that this equation is right. That is because dimension analysis will only consider the fact that if that equation is dimensionally consistent. So one drawback is that an equation can be actually wrong and dimensionally correct. The dimensional analysis cannot tell you if it is actually correct. So it can only check if an equation or a formula is dimensionally correct and not actually correct. So we can only check if a particular equation is dimensionally correct and not actually correct. The next problem is that if I write an equation like, let's say, t is equal to 2 pi root of L by G, then the problem is that this using dimensional analysis, we cannot figure out what is the value or what exactly happens to this particular constant. That is, if there are constants involved, if there are irrational numbers involved, or if there is trigonometric or exponential functions involved, we cannot analyze them using dimensional analysis. So that is one more drawback, that is, we cannot use dimensional analysis to analyze constant terms, trigonometric terms, and exponential, log terms, etc. All these kind of terms cannot be analyzed using dimensional analysis, and that is a drawback. One more drawback is that if there is a dimensional constant, it cannot be calculated. If there is a dimensional constant, it cannot be calculated. So that is one more drawback of dimensional analysis. So we have 3 dimensional drawbacks right now, that is, dimensional constants cannot be calculated, we cannot use it to calculate trigonometric or exponential functions, and we cannot calculate or we cannot see if an equation is actually correct. If I give you just the dimensional formula, we cannot say that that equation is actually right. We can only say that that is dimensionally consistent or dimensionally balanced. That is all about dimensions and dimensional analysis for today. I'll be back with more sessions. Until then, thank you.